Alright everyone, welcome to another Physics QBits video. This QBits video is a follow-up to our massless pulley video, in which we're going to talk about kind of what to look out for when all of a sudden we're in second semester physics and our teacher puts mass on our pulleys. God forbid, right? And so we'll just kind of go through a couple of quick conceptual ideas, and then we'll cap things off by looking at how those apply to an example problem, just like the last video. So, first, right, let's talk about why we make that massless pulley assumption. So whenever we have a pulley problem, our system is going to look kind of like this, right, where we have our pulley and we have some rope hanging down on both sides with maybe like an object attached to each one, right? And so earlier when we talked about why the massless pulley assumption was important, right, we figured out that having a pulley with no mass means that the tension on either side of the pulley has to be the same. Otherwise, you get infinite acceleration, right? But when we think about this from kind of a torque perspective, right, it's not just the tensions that matter. The fact that this tension is acting on this pulley at some distance r means that we're going to have a torque associated with this tension. We'll call it tau L, okay? And this torque is going to try to cause things to rotate counterclockwise. Similarly, the right-hand side of the pulley also has a force acting at some distance from kind of the rotational axis, right? And so we're going to have another torque, tau r. And so the massless pulley assumption is basically a simplification that the left side tension is equal to the right side tension. And this also holds true for the torques because the forces are equal, right? And they're acting at the same distance from the center. Then we have tau L equals tau R as well, okay? And these are two really nice simplifications because they let us basically completely ignore the dynamics of the pulley. But now, as soon as we have mass, we now need to actually include the pulley in our dynamics calculation. So if the pulley has mass, then we have to say that TL is not necessarily equal to TR, and the torque on the left is not exactly equal to the torque on the right. Because now we can't claim that the force transfer is kind of perfect here, right? We know that some of this force has to go into turning the pulley as well as accelerating the blocks that are attached. And so basically what this means is we need to include the pulley in our calculation, okay? We need to consider the dynamics of the pulley. Okay, so what I wanted to do was kind of do a quick example problem of a pulley that has mass and talk about kind of the points where this might be different than a calculation where the pulley doesn't have mass, okay? So for this setup, what we have is a pulley of mass, kind of this like block scripty M. We have two blocks hanging off either side of this pulley, one of mass capital M and one of mass lowercase m. And let's just say we know that the big M mass is heavier, and so this is going to cause this entire configuration to rotate this direction, okay? And our goal is going to be to find the actual angular acceleration. And so like before, we know that this is a pulley problem, and so our first step should be drawing a free body diagram because pulley problems really are force problems. The kind of wrench in the works here is that we need to consider the pulley as well, right? The actual disc itself. And so because the disc is a rotating object, it's a rigid body, we need to draw an extended free body diagram in order to understand how the forces are causing a torque on the pulley as well. So let's start with the first two free body diagrams for just the blocks themselves, because I think those are a little bit easier. Each of these blocks has a downwards gravitational force. So this block on the left has a capital mg force pointing down and a tension TL pointing upwards. The other mass, the mass little m, has the same forces but with different magnitudes. So we might have a little mg here and we have a TR here, right? And as a reminder, right, because this pulley has mass, then we know for a fact that this TL is not necessarily the same as this TR. Okay, so keep that in mind when you're setting up these free body diagrams. Next, we need to make a free body diagram for the pulley itself. And so the only things that are causing a torque on the pulley are the two strings on either side, right? And so we have our first string, TL, kind of applying a tension force downwards. And on the right-hand side of the pulley, we have our TR applying a tension force downwards this way, right? And whenever you're drawing an extended free body diagram, remember, it's important to label the distances at which these forces act relative to our kind of rotational axis here as well. Okay, so the only thing we've encountered here that I want to highlight, like we did before, is just that these tensions, right, are no longer the same because our pulley has mass. Okay, so in the usual prescription, once again, we want to write down our Newton-second laws for both forces, and because we have our rotating object now, we need to write down the torque Newton-second law as well. Okay, so like we talked about for pulleys before, one thing that I think is helpful is using the pulley to decide which direction is positive and negative, okay? Because in this case, I know that the system is going to rotate counterclockwise, it's kind of convenient to set my coordinates such that anything associated with this counterclockwise rotation, we can count as positive, and anything associated with clockwise rotation, we can consider negative, okay? Just like this kind of purple orientating diagram shows us. So if I look at the free body diagram for the mass on the left, I can write down my Newton-second law equations. And in this case, right, I can draw my little reminder. For this diagram, downwards is positive. So my free body diagram is going to give me an equation that tells me plus mg minus TL equals capital M times A, okay? Then I can look at the other free body diagram for the other mass, and I can see that in this case, right, the direction of positive is the other direction. It goes upwards because now this upwards direction is associated with the counterclockwise rotation of my pulley, right? And so my second equation is going to look like plus TR minus lowercase mg equals lowercase m a. And I'll label these AL and AR for now, but when we get to constraints, we'll see why it's not strictly necessary. Okay, and the final thing we have to do is make a Newton-second law equation for torque based on this extended free body diagram on the right, right? And once again, we can remind ourselves that any torque that goes counterclockwise is positive, and any torque that goes clockwise is negative, okay? So if I look at this equation, I know that the torque from the left rope is trying to cause my pulley to rotate counterclockwise, right? And so that means that the torque associated with TL, or tau L, is going to be a positive torque. We also know by definition that the torque is the magnitude of R times the magnitude of F times the sine of the angle between R and F, right? And when it comes to computing the actual torques, we know that the left torque is going to be the distance that it acts at, or in other words, R, times the value of the tension, the actual force, TL, times sine of the angle between these guys here, okay? Because the angle between the rope and the lever arm is just a 90-degree angle, this is sine of 90, which of course is just 1. And so we can write down that tau L is just R times TL, okay? For similar reasons, I can write down that TR is the radius times TR, right? But it's a negative value, okay? Because the this torque is going to cause the object to try to rotate clockwise, which is associated with our negative direction, right? And so if I collect these, I can say that the net torque is going to be tau L minus tau R, and this is going to tell me what the kind of angular version of Newton's second law tells us, the moment of inertia times the angular acceleration, okay? And what I can do is kind of just substitute my expressions for tau L and tau R here, right? So I know tau L is RTL, and tau R is R times TR, okay? And so going directly from our free body diagrams, I can get these Newton's second law equations, okay? And so, as per usual, what I want to do is kind of avoid thinking about simplifications until I get to my step 3 for constraints, okay? And so before we move on, I want to highlight something, right? Earlier I said that because we now have a pulley that has mass, we need to take into account the pulley's dynamics. that's what this equation here is telling us, right? This bottom equation. This is what relates the kind of forces to how those forces are going to turn the pulley, right? We can see that on the left-hand side, we have our kind of actual measurable TL and TR. And on the right-hand side, we can make some inference about the angular acceleration of this pulley, right? Okay, so let's move on to thinking about our constraints here, okay? I'm going to write these in purple because these are basically the pieces of advice I have for doing pulleys that have mass, okay? But the constraints that we can write down are a little bit different than the massless pulley, right? Before, we said something like TL equals TR, but because our pulley has mass, this is no longer the case, right? The other constraint that we had for the pulleys was that the acceleration on the left-hand side is the same as the acceleration on the right-hand side. It turns out this constraint still holds, right? As this pulley rotates, whatever rate the left thing is accelerating downwards at has to be the same as the rate that the right thing accelerates upwards at. This is still true because the rope is still taut and there's no bunching of the rope happening on the pulley, okay? The other thing that's interesting, though, is now that because the pulley rotates, we can relate these accelerations, AL and AR, not only to each other, but also to the rate of rotation of the pulley, right? If I have this wheel turning, and over some time interval, I get this kind of total delta Y, right, for my mass going upwards, then that's going to be exactly related to the rate at which this wheel is spinning. In other words, this kind of like delta theta, the internal angle that it cuts out. And the relationship we can write between delta theta and delta y is just that by definition of what a radian measure is, those two variables are related by this equation here, okay? And so what's useful is I can take two time derivatives on either side. So I'm going to do d squared dt squared of this whole thing, okay? And because this radius is just a constant, really I'm just applying my derivatives to delta y and delta theta. The result of this is that d squared y over dt squared, or in other words, the acceleration, AR, is equal to r times d squared theta dt squared. If I write these in kind of the acceleration terms, this just tells me that the acceleration on the right-hand side is equal to r times alpha, which by definition is this guy here, right? The second time derivative of the angle. And so what that means is I can relate AR to alpha as well. This makes sense, right? The amount of kind of lines spooling or unspooling from the pulley should be related to how quickly the masses are accelerating up and down. And so what that means is we can extend our constraint on the accelerations a little bit, okay? We can now include AR equals AL is also equal to alpha times r, where alpha is the rotational acceleration, okay, of the pulley that's spinning. And so this is the important thing for solving problems with pulleys that have mass, right? We want to be able to relate the rotation of the pulley to the actual linear translation of the masses that are hanging. Okay, so let's try substituting this constraint in, and then we'll take stock of and see whether our equation is solvable or not. Okay, so the first thing I can recognize is that I know that AL and AR are the same. So I'm going to kill the subscripts on AL and AR. And I also know that this alpha is related to A, right? So I know that because A equals alpha times R, I can rewrite these A's to be alpha times R and alpha times R. And so now the only thing that's measuring acceleration is this alpha. In other words, we're measuring the acceleration of the entire thing just in terms of how quickly the pulley is rotating. Okay, and so as per usual, let's make sure we have enough equations to solve for all the variables that we need, right? So we know both masses, so m's, all the m's we know. Because we know the disk's mass and radius, we know what this moment of inertia is, right? For a disk, I equals 1/2 block m r squared. Okay, so we know this guy. We don't know what the angular acceleration is, and we don't know what these tensions are. But if I look at this equation, right, I have my 3 equations, and I only have 3 unknowns. So strictly speaking, this should now be solvable. So now if we wanted to, we could move on to solving the equation. Okay, And so what we see is that when we're solving problems with pulleys that have mass, right, we lose one constraint here. We can no longer say that the tensions are equal, but we gain a new constraint in the form of this kind of right-hand side of the equation here. We know that the angular acceleration is related to the linear acceleration. So we're kind of net neutral on how many constraints we gain and lose. Okay, so I'm actually going to not solve this equation, this system of equations, because I think it's kind of cumbersome, and I promise you can do it, but I just don't want to spend the time in this video to kind of do the algebra. So I'll leave you to do that on your own. If there's lots of people who want to see this fully solved out, I'd be happy to make a kind of follow-up office hours video. But for now, I'll just leave this problem here. Okay, so let's talk about what we learned in this video. First, we know that if we relax the massless pulley constraint and we add masses to our pulley, then we know that we can no longer relate the tensions on either side. So remember, the massless pulley means that TL is equal to TR. If the pulley has mass, then this is no longer true, right? Okay, the other thing we saw was that when we're solving this problem with a pulley that now has mass, we need to include the pulley in our free body diagrams. Or in particular, right, we need an extended free body diagram because we need to consider the torques on our pulley. And finally, the last thing we saw was that whenever our pulleys now gain mass, right, we need to somehow relate the acceleration of the pulley to the accelerations of the masses so that there's something that kind of ties them together. In this case, the acceleration of the pulley, alpha, is related to the acceleration of the masses, which we'll call A, right? So we can kind of extend our constraint on the accelerations by saying we know that AL equals AR equals alpha times R, where this is the angular acceleration of the pulley, and this is the radius of the pulley. And remember, this relationship is really about how if I unspool some amount of wire, the amount of wire unspooled, or in this case delta y, is related to delta theta by the same relationship. Delta y equals r times delta theta, right? So this is another restatement of the idea that we can kind of translate between the amount of angle that this pulley turns through and the amount of wire or string that it kind of spools up. And so just like the other pulley problems, right, as long as you keep in mind these new constraints, if you just go through the usual four-step process, this should be enough to kind of get you to a solvable system of equations every time. And so, cool, that's really all I have for this video. Like I said before, if you want to see this problem worked out in full, just let me know and I can make an office hours videos showing you how to actually solve the rest of this problem. As per usual, if you have any thoughts or questions, or you want to challenge me with another kind of pulley with mass problem that you want to see worked out, I'd be happy to address those in the comment section down below. Other than that, please don't forget to like and subscribe for more free physics problem solving tips. This has been Physics Tutoring Quantized.